things here we have to do is to make it cheaper so that it's more accessible for everybody. Then from detector experiments from detectors, the imaging, that means how you register particles, you can also use it for PET, for the PET scan. And this is a 40 years work since the 70s roughly. We have a very good connection with the Hôpital Cantonal in Geneva to improve the instrumentation on the PET scans, and even since 10 years to allow to combine PET and MRI by instruments which you can read out in the magnetic field. So this is a give and take between basic science and application. So this is a very exciting field which is emerging more and more also at CERN. Okay, now to physics. Particle physics and accelerators. We essentially address two questions. We want to explore the innermost structure of matter by looking at the questions: which are the fundamental constituents of matter? And which are the forces which interact between them? These are the two basic questions. Now, by investigating the structure of matter, by addressing these questions, we gain understanding of the early universe. Oops, this was the wrong button. Okay. What is the role of accelerators in that sense? Well, they play the role of super microscopes. The higher the energy, the smaller the wavelengths, that means the better you can resolve the inner structure of matter. The higher the energy, the higher the masses of new particles which you can produce. So these are the key issues. These are the key issues concerning accelerators. High energy for resolving and for producing new particles, and high statistics, that means in our high luminosity, high brightness of the accelerator, in order to do precision measurements. You need, of course, a lot of statistics to do your measurements. How do we do the acceleration? Well, you can only accelerate charged particles like protons or electrons or the antiparticles. So acceleration, of course, happens through electric voltage. Suppose you have a voltage of 1 volt, a proton, then this proton has a charge E. It gains the energy of 1 electron volt. Now at the LHC we are running with TeV energies with 2 times 7 TeV. 1 TeV is 1000 GeV, is 1 times to the 10 to the 12 electron volt. So if I would do it with batteries, I would need 14 batteries per star in the Andromeda galaxy. Of course, we do it slightly differently. In order to address one of today's scientific challenge, namely to understand the very first moments of our universe after the Big Bang. So from the Big Bang to today, it's roughly 14 billion years, and the universe has expanded from essentially point light to 10 to the 28 centimeters. Well, frankly speaking, I don't know what that is, 10 to the 28 centimeters, I cannot imagine. Now, when you replace the centimeter by dollars, then you roughly have the square of the American deficit. I don't know if that helps you to imagine the size. It didn't help me very much, but I think those numbers are impressive. Okay, you can also put it differently. This is the size of the universe today on a ruler from the Big Bang up to today. It's very difficult to imagine the large numbers. It's equally difficult to imagine the small numbers, because from a certain point onwards, for me the numbers 10 to the minus 16, 10 to the minus 20, for me that's close to 0. So I cannot imagine the differences between in the sizes. What we can imagine is the center, of course, the human dimension. And I've put here Rutherford because last year it was 100 years of Rutherford, of the Rutherford interpretation of the experiment. And it was the start, to my mind, of nuclear physics and particle physics, because at that time we found out that we are essentially empty because the atoms consist of very small nuclei. So today 100 years after Rutherford, we can look into the large scale of the universe with space-based telescopes, for example, or ground-based telescopes. Or we can do it on the other scale with a super microscope, like the Large Hadron Collider, looking at the small, very small sizes of the particles, the smallest particles we can resolve, and we get down to 10 to the minus 16, 10 to the minus 17 centimeters. So we come relatively close to the Big Bang in time. If you recalculate it and then calculate it in time, we come as close as 1/1,000,000 of a millionth of a second to the Big Bang. It's pretty close. It's pretty close in human dimensions. It is a long, long time in the development of the universe because much has developed in this very, very short time. And what we have learned in the 100 years now is from Rutherford, who found out that there is a nucleus inside the atoms. Now the nucleus consists out of protons and neutrons, and these in turn then consist out of quarks and gluons. So the protons and the neutrons are not fundamental particles. The fundamental particles are the quarks and the leptons. Now the fantastic thing here is that when we study the physics laws of the first moments after the Big Bang, we have a fantastic symbiosis between particles physics on the one hand side, astrophysics on the other side, and cosmology. And this is really which brings these questions, these intriguing questions, bring the students into physics. Then they go to other areas. This is fine, but they start studying physics and start becoming physicists, researchers, or engineers. So we need these intriguing questions in order to trigger people to study natural science. Okay, so one step back. What I have to tell you, since not all of you are particle physicists, I guess I'm the only particle physicist in the room here. A little bit more what we know about the fundamental particles. Well, what are the matter particles? We know today that matter consists out of quarks. Here is the up quark, the down quark, and the leptons, the electron and its electron neutrino. This indicates a little bit the mass scale. So the electron has less mass than the down on the up quark. And I've put the arrow here because the neutrino has a very, very small mass. This is all we need. All of us, all of you, the chairs where you're sitting on, everything consists only out of the up and down quark and the electron. That's all. Nonetheless, we are pretty different. Anyhow, that's all we need. Now you see there's a lot of space left. Nature has decided to introduce a second family. Exactly the same thing. 2 quarks, charmed strange, and 2 leptons, the muon and the neutrino. So these guys are brothers or sisters or cousins of the first family. And the only difference here is, the properties are the same. The only difference is the mass. The second family is much more massive. Now nature has also then decided to introduce a third family. Again, the same properties, and 2 quarks, 2 leptons. And now you can imagine what happens. Huge difference in mass. Actually, the top quark here is as massive as a gold atom. Nonetheless, it's a point-like particle, it's a fundamental particle. It's difficult to imagine, huh? It's a point-like particle, nonetheless, it has a mass of a gold atom. So, it's fantastic. So this is what we have learned over the past 40, 50 years. The physical world is composed out of quarks and leptons, the 3 families, 2 quarks each, 2 leptons each. And they interact via force carriers, the gauge bosons. The photon mediates the electromagnetic force, the gluon, the strong force, and the Z and the W, the weak forces, the weak force. These 3 forces are mediated by these gauge bosons. That's all. That's the periodic system of the microcosm. So in principle, particle physics is much easier than chemistry. We have a much easier periodic system. So, but that's the static picture of the microcosm. The dynamics is described